Okay, so our next speaker is Professor Rebecca Kramer-Bottiglio from the Yale University, where she runs the Fabratory, researching new and innovative ways to make things. So Rebecca, if you'd like to share your screen.
Yes. Can you hear me okay?
Yes, we can hear you great. Thank you very much.
Awesome.
And you can see your screen. Brilliant. I will hand over to you. Thank you very much.
Great. Thank you. I'm going to, here we go. I'm going to minimize you. So if there's any problem with the video or audio, please just interrupt me so I'm aware.
Will do.
Thanks. So thanks, Josie. Thanks to all the organizers for the invitation. I'm really enjoying this workshop. In an attempt to really embrace the theme of this workshop, I'm going to go a bit offbeat from my usual talk format, and I want to play a bit of a game called Is It or Isn't It Embodied Intelligence? Okay, so let's start with what is embodied intelligence. I think that's what we're all here to figure out. At least that's definitely what I'm here to figure out. So the first thing I did when I started preparing for this workshop was just look up definitions of embodied intelligence in the literature, and I found this one that I quite like. Natural life thrives in unstructured environments through a specific brand of intelligence known as embodied cognition. Intelligent behavior emerges from tight coupling between an agent's body and brain and the environment, not solely from the brain. Okay, so my initial thought when I was reading this definition and many others is, well, this sounds an awful lot like morphological computation. Okay, so what is the difference between embodied intelligence and morphological computation? So then that led me down the rabbit hole of looking at many definitions for morphological computation. And I'll put this representative definition up here. Morphological computation can be loosely defined as the exploitation of the shape, material properties, and physical dynamics of a physical system to improve the efficiency of a computation. Okay, so these sound pretty similar to me. So then something really helpful happened. I had a phone call earlier this week with Dan Goldman, who is presenting right after me. So I think he's presenting right after me. And we were pondering this question: what is the difference between embodied intelligence and morphological computation? And Dan had the idea to look up the very literal definition of intelligence. So according to the dictionary, there are two primary definitions of intelligence: the ability to learn or understand or to deal with new or trying situations, and the ability to apply knowledge to manipulate one's environment. Now, this gets a little bit nuanced, especially after yesterday's talks that I attended and put forward, an interesting definition or an interesting contrast between physical and computational intelligence. And Hod posed a definition of self-awareness, the ability to imagine yourself into the future. So weighing all of these together, I'm going to put forward these two potentially oversimplified and maybe even incorrect definitions, and I hope this can spur some discussion. Morphological computation is the idea of reducing the amount of compute necessary to perform a task by offloading some to the agent's body morphology. And embodied intelligence is the idea of embodying an ability to learn or apply knowledge. This is a direct substitute from the definition of intelligence, which could include adaptive agent morphology. Now, these are potentially very self-serving definitions because one of the core themes of my lab is developing shape-changing robots that are capable of adapting their morphology, properties, and behavioral control policies to changing tasks and environments. So at the highest level, my group is working at the intersection of materials and robotics. We actively leverage material discoveries to push forward the functionalities of the capabilities of soft robotic systems. So in this short talk, I'm not going to talk at all about the materials, but rather I'll focus on a few shape-changing robot examples and try to argue both for and against why they might be representations of embodied intelligence. So the first couple robots I'm going to show are based on the concept of robotic skins. Robotic skins are planar, soft, elastic membranes with embedded actuation and sensing, which can impart controlled motions onto the objects that they're wrapped around. So for example, you could wrap a robotic skin around a moldable material, something clay-like, and apply surface strains and pressures to mold the morphology of the underlying body. So this is what we've done here. Here's a robot made from robotic skins wrapped around moldable clay-like material. This is Model Magic. And this employs both a pneumatically driven skin and a cable-driven skin to locomote and shape change, respectively. So the robot is initially in a cylindrical shape, and it uses sequential inflation of its pneumatic bladders to roll forward, and then it encounters an obstacle, a rock. So when it encounters this obstacle, it cinches in the middle using its cable-driven skin to morph into a dumbbell shape, and then it's able to continue locomoting over the obstacle. So this demonstration shows how an editable robot morphology can be used for obstacle avoidance tasks, allowing the robot to change only its morphology while keeping the same path and control policy. All right, so here's the game. Is it or isn't it embodied intelligence? I argue that this robot does represent embodied intelligence because rather than changing its path or control policy, the robot adapts its morphology to an environmental obstacle. So this morphological responsivity to the environment is in line with a tight coupling between the robot body and its environment. I also argue that this robot does not represent embodied intelligence because it's not actually intelligent. This robot is controlled by an off-camera human, and it's not displaying any autonomous intelligent behavior driven by the materials or otherwise. All right, so on to the next example. Here is a similar shape-changing robot, which uses a pneumatic body to switch between a cylindrical shape and a flattened shape. So the robot uses these different shape gate pairs to navigate both a flat and an inclined environment, demonstrating the concept of gaining environments through shape change. So I'll note that the most interesting thing about this robot is that it was designed in simulation by evolutionary algorithms. So for this work, we teamed up with Josh Bungard at UVM to test a multi-objective optimization pipeline using evolutionary algorithms, which was able to simultaneously optimize the robot's shape, control policy, and orientation. So the algorithm discovered that a cylindrical shape rolling on flat ground is pretty optimal, and a flattened shape crawling up an incline is pretty optimal, which sounds intuitive, but we went a little bit more granular with the study. So we used the pipeline to find the incline value where the locomotion strategy switches. So we proved that crawling is not universally better on positive inclines, and rolling is actually favorable on small inclines. All right, so is it or isn't it embodied intelligence? In this work, we set out to test the hypothesis that shape and controller adaptation may improve locomotion speeds across changing environments more effectively than controller adaptation alone. And we found this to be true both in simulation and in reality. The heavy dependence between the body shape, the gait, and the environment makes me think that this example is more representative of embodied intelligence. However, in the physical instantiation, the evolutionary algorithms are not on board. And as I understand it, search-based learning on the fly is an incredible challenge. So the physical hardware version of this robot is also not autonomously intelligent. Okay, so now I'm going to switch gears to robotic fabrics. As a general motivation behind this work, I'll note the ubiquity of fabrics. I'm currently wearing fabrics. The chair I'm sitting on is covered in fabric. Fabrics are all around me, and they're usually used in applications that require flexibility, breathability, a small storage footprint, and low weight. And the idea of roboticizing some of these fabrics is appealing. So towards this goal, we developed a set of functional fibers made of multifunctional composite to embed actuation, sensing, and variable stiffness functions throughout conventional fabrics without losing the advantageous properties of fabrics, such as their breathability and fiber architecture. So integrating these functional fibers into a fabric, we can demonstrate a move and hold shape-changing operation. So here you can see this robotic fabric turning into a load-bearing table-like platform. The initial form is flat, and upon activation, the fabric softens its variable stiffness frame and lifts itself up. We then cooled the variable stiffness fibers to make the shape rigid and load-bearing, which you can see when we put the weights on it and it's able to hold those weights. We then apply a current to warm the variable stiffness fibers again, which softens the frame, and the shape is returned to its initial flat configuration using antagonistic actuators. All right, returning to the game. Is this or is this not embodied intelligence? I think I can make an argument that the distributed functionality in this robot is a form of embodied intelligence. The distributed actuation, sensing, and variable stiffness fibers show the concept of multifunctional materials more deeply embedded or integrated into the robot, which is embodiment. On the other hand, there is no autonomous intelligence on board this robot, and the changing properties and shapes are human controlled. All right, so I'm now going to switch to the final example of my talk, morphing limbs for amphibious locomotion. So this project is motivated by the challenge of traversing the shoreline, where there are three distinct environments. There's relatively stable open water, there's dry land, and then there's the in-between, the surf zone. Efficient locomotion in each of these environments is usually drastically different. Animals are typically optimized for locomoting in the water or locomoting on the land, but not both. So our concept is to leverage two related but distinct animals, sea turtles and land tortoises, to create a morphing limb which can transition from a flipper optimized for swimming in water to a leg optimized for walking on land. So these limb changes combined with traditional motors mounted in a turtle-like shell enables the robot to locomote both in water and on land. So I'll start by showing you some videos of the robot swimming. Let me just click these to get them started. So this is obviously not our robot. This is a real sea turtle for comparison. But here you can see our robot performing some representative swimming maneuvers. So we're testing both lift-based and drag-based propulsion strategies, and these are really early tests. So the gates are by no means optimized. We're still working on fundamental challenges like buoyancy control and wireless communication in multiple mediums, but you can get a sense here for the different aquatic maneuvers that we've tested, including submerged lift, surfacing, and diving. And right now we're in the process of optimizing these gates and quantifying cost of transport. All right, and here is the robot walking. So we've morphed the limbs into a leg configuration out of flipper configuration, and we've tested two gaits on land. The first is a creeping gait, which is what the robot is doing here. The creeping gait is loosely inspired by the motion of land tortoises. However, our morphing limb does not have a knee joint, so they're not strictly analogous. Here you can see the robot creeping on our tiled lab floor and on a compact mixture of sand, pebbles, and water. However, this gait did not work on loose sand due to slipping, but here we can watch the robot locomoting on loose sand using a different gait. So in this gait, the limbs are splayed out and the robot is in contact with the ground, which distribute the robot's weight over a larger area and prevents the legs from slipping out. And perhaps we can all see the inspiration for this beach crawl gait, which is what the real sea turtles are doing here as they crawl up the beach. Right, so is it or isn't it embodied intelligence? So as an argument for why it is, adaptive shape and control policy of the robot allows it to traverse drastically different environments and locomote efficiently in these different environments. And that allows us to use this platform to begin asking interesting questions like how and when should a robot change its shape and gait when transitioning from one environment to another. As with all the other robots I've shown, though, I think it's difficult to claim that the current robot truly embodies intelligence, since all of the control and the transitions are pre-programmed or done by a human with a direct line of sight to the robot. Okay, so I want to end on this final question, which is a question that I started asking myself as I prepared this presentation. Are all shape-changing robots examples of embodied intelligence? So using a definition that my group put forward in collaboration with Josh Bungard and Mike Levin in a recent review on this topic, I do notice some commonalities between our definition of shape change and the definition of embodied intelligence that I started with. So I'll leave this as an open question that can hopefully spur some discussion. And so I'd like to wrap up there by thanking my group, my funding sources, and thank you for your attention.
Thank you very much. That was really interesting. And I love the going back to the definitions. And it's a really interesting question. Does something have to be autonomous to have embodied intelligence? Can it be human controlled and just have that in the physical body and still show this embodied intelligence? So thank you very much. And I'm sure that's going to be a really great starting point for discussion in a few minutes.